There you go.
Hey,
Splendid. Now I can't annotate anything. That's fine. I'll use my finger. Graphite, like the collaboration recently started the fourth observational run. So what they did is they upgraded the facility that improved the sensitivity. Hopefully, we detect more and more gravitational wave event. It'll last for about 20 months with some intermission. And so what's so special about the newest observational run is events are coming in hot. There are more and more gravitational wave events coming. Last night I checked, it was 38, 47. So if you do F5 anytime, it may update. This is like real time, like their trigger and alert. So whenever there's a new trigger or an alert, they will get sent to this page. You can see how horrible we are in determine where these sources are. This is like basically the heat map of what's the probability of the events coming from this garbage. But anyway, the sky map is not the point. It will tell you whether there's a binary black hole or not. But for people who are in the field, which to my understanding, there's none. How do I mean in there? I don't know. People that keep up with the number of how many detection are there in our catalog, 38 in a couple of months is down crazy. Because in the previous catalog, the total number that like the previous observational run has lasted a couple of year and a half, I think, the accumulated time. That's about 100 events, and in just a couple of months we already get 40. And so the instrument actually works, the upgrade actually works, and it's delivering great number of events. So we have more events to work on statistics, more crazy event that LIGO is going to tell us more about. So we're entering an era that we can finally start to do some sensible statistics. Because at the very beginning of LIGO observation, we have one event is okay, let's do some statistics. You can do that, but it's not great. But now we're getting into the era which you can do something more sensible. Okay, so there are more and more events, and there's an even brighter future on the horizon, which are these so-called next generation detectors. They're Einstein telescope, which is a Europe-based effort on the ground across 3 countries. Cosmic Explorer, which is a US-based effort that to just scale up LIGO. Now our arm length is about 4 kilometers. They're just like, let's just make it bigger, 40 kilometers. So then it will get you more stuff. And there's also joint US and Europe effort to launch LISA, which is just something in the space trailing Earth to detect another class of a whole different window of gravitational wave. And these next generation detectors are really spectacular in the sense that I was talking about how 38 in a couple of months is not revolutionary, but very exciting to the community. But the ground-based detector, like on the left, this is kind of like the horizon of what next generation ground-based detector are capable of. So we are smaller than A+ right now. A+ is the design sensitivity of our current facility. That these are the horizon for different classes of source. So it could be a binary neutron star black hole, or binary black hole. So the current facility at its design sensitivity will detect a couple. The dot is somewhat random. But like the density of point is to scale. The absolute count is not to scale. But like we barely detect, some number. Okay. But when we reach the next generation detector, basically this horizon is saying, as long as you have something merged in the universe, we'll detect them. And that's crazy. You have a detector that will detect every single gravitational wave event in these classes, every one of them. So that's nuts. And they supposed to deliver millions of events, well, roughly 1 million events per year, which is beyond imagination. And we'll actually get to why that is crazy. It's not just a blessing, but also a curse to the LIGO engineers. And
what's Voyager?
Voyager, like this is Voyager. It's like some intermediate, like 2.5G or something. People are thinking, should we build this? Should we not build it? But it's called a Voyager. We don't talk about that. We're like next generation things. That's what people focus on. Because like, why should we build something in the middle? What's the exact reason for that?
And the numbers are in what time period?
This is like the absolute count of these dots is not very meaningful. It's just, I think it's normalized some unit time. I don't exactly know.
Puzzling is it why they're so higher density.
Oh, so I think like first off, I think neutron star it's more abundant because of like initial mass function, something like that. You're more likely to get
In
neutron star.
practice, we've seen very many fewer of those than black hole.
Yeah, well, I mean, you mean right now, or because
I mean, they won't be relatively more detectable later, will they?
I mean, like the reason why we detect more binary black hole now is because they're louder. So we're not in the region that. So you can see, like within. Well, actually, this figure is not great for illustrating that. But so far, a neutron star, we don't have like a large enough volume for many neutron star. I think we are like our sensitivity is about. In O1, it's about 40 megaparsec. Like the first binary neutron star is about 40 megaparsec, but the first binary black hole is about 400 megaparsec. So the volume vectors from binary black hole just happens. It's the selection function of detecting.
If you look at the dot dash purple curve, for example,
Yeah,
it extends beyond all the neutron stars you ever expect,
yeah,
right? In whatever model this is. Whereas for the black holes, it extends much further. You don't get any more black holes because there's no more black holes out.
yeah. Like so the idea of this figure is so this is, well, I mean, we haven't seen these. So it could be you reach here and there's no binary neutron star. There could be a universe that we live in. We don't know. We build an instrument, we'll figure that out. But this is what people like the theorists have think. Okay, given a cosmic evolution history,
That
yeah,
part of it, I'm
yeah.
trying to understand, there's some selection.
Yeah.
aspect, Otherwise, it wouldn't be unbalanced like that, because you must be saying that the selection
Yeah.
is changing, because right now, we see
Yeah.
many more.
Yeah, like right now, we haven't completed the volume, and we are more sensitive to heavier mass, much more sensitive to heavier mass, like around 30 something. Like beyond, like I think from 30 to 60, you're pretty completed. Where our horizon goes to like redshift 1 and beyond redshift 1. But our horizon for VNS right now is around 0.1 to 0.2. So it's like much more stringent, and we haven't reached that volume yet. Does that make sense? Okay, good. And on the right hand side, it's again, any question, feel free. No. On the right hand side is the so-called noise plot, or the PFD overlaid with like a number of target sources for LISA. So keen observer will notice the frequency is actually not the frequency where LIGO live. LIGO live in this window, okay? And LISA is designed to crop a lower frequency range than LIGO, and lower frequency usually mean like larger in scale. So or like earlier or something in an in-spiral, and the y-axis is just strength, like some measurement, some characteristic strain for the system that we're targeting. So you can see the target that we like LISA is mostly going to focus on is these supermassive black hole merger, black hole binary merger. And there are a number of other classes of events, such as binary white dwarf, something called Emery extreme mass ratio in spiral. But these are systems that it like for supermassive binary black hole, they are much larger. So the length scale is longer, and we detect their merger. But for things like white dwarf or Emery, it's more like the in spiral phase, so before they collide. And that should tell us something about galaxy formation, like seed of where galaxy comes from and stuff like that. Anyway, so the idea is like they're gonna detect another class or another category, another window for gravitational wave. So the future is right. If you grad student, something like that, it gets you funding, so good. Anyway, it's something to think about. So that's great.
And these curves mean that these supermassive systems will be in the bandpass for months or years.
Depending on which mass you're talking about, but yes. So this is like how long, like these marks basically say how long they're gonna be in band. As you scale up in mass, you go up in strength, but also you go to lower and lower frequency because the length gets bigger. So they shift out of band.
I see.
Yeah. Good question. Okay. So that's the landscape of gravitational wave and where are we now and where it is heading to. What are the problems that people are dying to solve? So one class of problem that people are trying to solve is searching. Okay, so gravitational wave is basically a time series, right? Like well, actually it's much more complicated than that, but let's for the simplicity, we're gonna say it's a time series. So okay, you have strain, you monitor as a function of time, and you can do a spectrogram of them. There's also crazy noise that you can find in the detector. There's like some backscatter of light. Sometimes there's like some bird land on an impact on your tube, and you get extreme loud, and you can have like
I'm
random.
gonna take you up on your offer. What is the x-axis? What is the y-axis?
So here, so I think here x-axis is time, y-axis is frequency. So this is the spectrogram. So you take your time series, you do short time Fourier transform. So for a specific window, you do like a Fourier transform, and you get the color is basically the power of that particular frequency bin. Sorry about that. So this is saying extreme now is basically in this time window across all frequency, you have like some crazy stuff going on. And where's a blip glitch? Blip glitch is in a very short amount of time, you have some power across all frequency range. And this is a particular frequency that is spamming you across a region of time. Something like
Are
that.
any of those actual gravitational
No.
wave events? Even that chirp one is not a real event.
No.
So these are all
Yeah.
false positives.
Yeah, if you, yeah, I think they're all possible. Yeah, I think this is I get it from a project called Gravity Spy. It's similar to Galaxy Spy or something, like Galaxy Zoo. So just like, basically they use a citizen science project that they want to give this image to people, classify them, and then you later on train a machine learning. I'm a big fan of citizen science project, but there's a reason why I wouldn't.
These
Going.
were just concocted, somebody imagining what they might be like.
Yeah, like, well,
Do you understand, are
So-
these coming from some sort of model or?
well, no. So this is okay. I don't usually touch like glitch and detector characterization. This is a whole team that's doing that. And there's actually the collaboration meeting happening in Japan. And one of my colleagues sent me a message like, hey, we really need your stuff. Like these people don't know what they're doing. But like, basically the way that we build a glitch model is like, we look at this and it's like, we think whether this is a gravitational, it's really like human driven effort. There's some likelihood that you can form, but it's not very, it's a lot of human.
But these particular plots are examples of real
glitches.
things that happen.
Yeah,
And these are experimental results, and they've just been classified
yeah.
as
Yeah.
signals to.
Well, one thing that I should say that, there are some more systematic way to classify what is a glitch or not. For example, if you see this in one of the detectors, you say, okay, maybe that's a gravitational wave. But a bubble going off in one detector does not necessarily trigger another bubble in another tube that is across the US. So you need to do some coincidence. And there are experimentalists that goes in and really perturb the system to see what kind of response the detector has to come up with this classification. So when I say, there's a lot of human, I don't mean that they're like big science. I'm just saying there's a lot of human effort going into just manually looking at the data, thinking, is this one? No. And they put it in a logbook. There's a lot of that. Whether we can be more systematic, that's something that's open.
So these are not things that have been detected in both.
This is
Just a single detector.
Uh,
I'm just having trouble understanding what you're showing us. So
well,
when
this
you
is
said that-
glitches. This is glitches.
But what constitutes a glitch? A single single station or both?
So by definition is I think it's more one, but it can happen simultaneously, but they don't necessarily have to agree with each other, right? Like you can have this one that happens in one of the detector and another one that happens in another detector. They won't be formed into a coherent trigger. So people do like different level of filters. So glitches can happen in any detector or like an earthquake, but we have a lot of sideband to monitor that. For example, if there's like some earthquake across the US somehow that is detectable, LIGO is like super sensitive detector, so they can sometimes pick up something like that, but then you monitor that.
I understand
Yeah.
the story. I wanted to know what you were showing us.
Oh, it's just an example of like glitches. But like it's in a particular, well, I put this like from illustration paper, so I don't know exactly whether they're both in both detector, but it's more likely, if I have to bet, they're more likely coming from one detector. Because if it is two detectors, I need to show you two graphs. Does that answer your question? Okay, good. So searches is actually not what I work on. The other thing that people are working, so people have been building, you see an image, so people have been using human to classify them. So what about we use machine learning to classify them? People have been doing that. I'm not going to go too deep of that, but you can imagine you can take this and deploy some image detection classifier to get some of the classification down. So you can do that. I'm not going to talk about that. The next thing that like people are looking into is making simulation with machine learning. So this is again, like this is an illustration from a collaboration work called SXS that show, I think it's the simulation of the first event. So basically this is, I'm just illustrating that there are people that's trying to use some machine learning to either make numerical relativity simulation, which is what's shown here, one of the illustrations, faster, okay, because the more simulation usually cover your parameter space better or something like that. Or actually not a lot of people trying to make them more accurate, which is something I want to do. But anyway, so some people are trying to pour effort into making simulation faster with machine learning. Not going to be the main subject of the result. The main subject of the result that I'm going to of the topic that we're going to talk about is inference. So what is inference? Inference is like you show me some data, for example, like my time series, then I'm trying to understand what causes that. Okay, the illustration. Okay, it has nothing to do with gravitational wave. But that's the fundamental idea that I work on a lot, and I've used machine learning. Some success, some failure. Let me know how I'm doing in time.
Oh, you got 40 minutes.
Yeah. Okay. Fine.
There's a clock up there. If you're ready.
Oh, okay. Cool. So the rest of my talk is mostly gonna be inference. What is inference? Inference is you give me the data, tell me some properties about an uncertainty about the system. Okay. Good. So there's a couple ways that people use machine learning to trying to do inference and speed up inference in gravitational wave. And the first part that I'm going to talk about is like some success called simulation-based inference. The idea of simulation-based inference is relatively straightforward. There's a lot of detail that goes into it, and these are two examples. It has nothing to do with gravitational wave. So what is simulation-based inference? Simulation-based inference can be like kind of follow the same following pipeline. So if you are able to simulate something, for example, in the cosmology simulation, if you can simulate or observe it, well, actually no. If you can simulate galaxy cluster distribution, right? Then if you can simulate a bank of them, then you can use an AI, whatever emulator, some machine learning algorithm to try to create an emulator that quickly produce a lot of this simulation. Then you just compare the simulation directly to whatever data that you observe, okay? So if you can simulate it, then you can train an emulator, then you can compare very quickly. The same thing that people do in collider physics, right? Instead of forming an explicit likelihood, like you write down all the term, what people do is, you build a simulation of your detector. If I have jets that coming in this way, the detector will look like that. Then I can build some sort of machine learning algorithm to try to emulate that very quickly instead of running the simulation, because simulation is usually expensive. And then once you have like built a grid of simulation, train your machine, then you can quickly compare whatever data that you get. Okay. So the trick here, the good thing about simulation-based inference is usually you don't need to explicitly write down your likelihood. You don't need to make specific assumption. Is my likelihood Gaussian or like some other follow some other statistic? The only criteria that you need to do in simulation-based inference is like as long as you can simulate a system, you're good. Okay. And how does that manifest to gravitational wave? So the problem that we're trying to solve in gravitational, let's go back to the thing that I actually know about. So the problem that we're trying to solve in gravitational wave is the following, right? So on the x-axis is time, on the y-axis is some White string. Again, this is an illustration. So bear with me. The dark blue is some simulated data. Okay, and after the white, we whiten it. And the cyan is the signal that we're trying to look for. So you can imagine this is a very small signal. So it's very hard to find. And actually, this costs, I'll actually get back to this later. But this costs millions of dollars for LIGO to do it. And there's a couple of very good reasons why this problem is particularly hard. And when there is a hard problem that is like, not completely solved, then people are trying to throw machine learning at it. And what we want to get out of this is so-called the posterior of the sources that we're trying to invert. Okay, so if you believe this, we were trying to do a GR experiment. We believe there's the source that we're trying to measure is, let's say, a binary compact object coalescence. That's the technical terminology, but really it's just like a binary coalition. That consists of a binary, right? So you have primary mass and you have a secondary mass. So the question that I'm trying to ask is, given the data, tell me the mass, okay, and the uncertainty. So this is like the probability of the mass that from this particular event. Okay, that's the task. Are we clear? Good.
And is that signal to noise ratio typical for LIGO events? That's just an illustration, but is that typically what the?
I think the floor is lower. I think the floor is lower. Yeah. Yeah, like so this is a pretty long, like if you want to actually get the SNR out of this, you need to do an integration. And this is a long signal.
Yeah.
So it's probably actually louder than that because like this is coherent and where noise is incoherent.
Yeah. So
you can integrate it out, filter it to have a pretty good signal. And but yeah, again, I don't know, like by eye, I think the signal to like the noise floor that we have is probably the absolute minimum that get registered as not a noise in a trigger bank is probably smaller than that. So this is not hopeless. You get it. Okay. So we want to do this fast because again, we have millions of events coming in, so we need to do this fast. All right. So there's some emulation and simulation-based inference techniques that have been poured into that. And this is a Twitter feed, that follows a paper that is not by mine, but it's good work. So I want to like advertise and show some good work that like machine learning works. So what they do is they generate a lot of simulated noise. Okay. Then because we can simulate gravitational wave event, we can create big data. Then they train a network to quickly reproduce that noise plus signal. Okay. Then once you have trained some model to quickly replicate that, then you can compare with data, and then you can say, is this one correct? Is that one correct? No. Then you can falsify what masses are allowed, and they can quickly turn out a posterior, which is fairly complicated. You can see a couple nice feature about them. Can have pretty wacky posterior stuff like that, multimodality, and this is reasonably high dimension. It's not very high, but it's not a small dimensional problem. And Max, a student from Max Planck, I think, can do this in 1 hour or so with like a decent GPU. Okay, I'll actually come back to like like bear in mind, like 1 hour is what they can do. Take a guess of what the typical time for making one event, like making one posterior, given the LIGO. What can the LIGO people do? Maybe we should do a poll later. Just like let's see how people estimate the typical time for coming up with one posterior in LIGO. Okay, later. But like now, I'll tell you this is 1 hour. This is what machine learning can do, like Max can do. Great work, love it. Okay, amazing. And the other thing that you can do simulation-based inference on is not just on one event. So if one event is hard enough, what about multiple events, right? So one thing that people are trying to do is to understand the population. So there are simulations that you can evolve stars, binary star, forward in time and make binary black holes out of them. And of course, that takes a certain amount of time that is not exactly trivial. And to really be able to simulate forward and then do inference will allow you to place constraint of what process goes into the evolution, right? Okay, so that's something that people want to do. They want to simulate a population of binary events, then compare with the data, compare to our catalog. We have 100 events. Is this consistent with my simulation? That's something that people wanted to do. So we actually, this is a paper by me. So we did that. We took a couple simulation, and so Cosmic is one of them. It's actually by a postdoc in CCA, Katie Breivik. She was a postdoc that evolved binary black hole in isolation. Okay, you can come up with some distribution of mass. Okay, you can see x-axis is the primary mass, y-axis is some density. So if you believe Katie, you believe her simulation, you'll get some distribution of mass. We can then take this distribution of mass, compare with what we observe, and we can place some constraint on what's the physics behind our catalog, what's the origin of the event that in our catalog, right? And this is just mass ratio, which is like showing two different aspects of the same set of events. And we took another simulation, which is a cluster simulation. So these are binary star that evolves inside a cluster. So no longer isolated, but in an environment that interact with each other. And you can see they have like different behavior. Right now, the mass is goes to much higher, and you have like a peak and stuff. But to compare these to the data is not exactly trivial. So we build emulator, we simulate this, we train some machine to emulate them and compare with data. And at the end of the day, we get posterior in whatever these parameter space. So this alpha is parameters that belong to cosmic that tells you how one process called common envelope, how efficient that could be. It's a parameter that basically tells you some properties about cosmic. RV is the typical cluster size, basically, if it is formed in a cluster. And F is the mixing fraction. Well, but like the idea of this plot is really to show you, even though we don't know how to exactly compare cosmic and CMC and our simulation with our catalog of data, as long as you can simulate it, you can run some machine learning thing, you can get some posterior. Okay, that's the message.
So, I mean, I guess. So for simulation-based inference, I mean, in all these cases, you're using an emulator.
Yeah.
You don't have to do that. You just use simulation, right?
Mm.
But also, I guess, remind me in the inference part, what exact, since you're not calculating likelihood, what is it you actually do to get?
Well, it's not like we always have a likelihood. It's why either you explicitly write down a likelihood or you have an implicit likelihood. Well, in this case, we actually, so I'm cheating in talking about this because we still have an explicit likelihood because I like hybrid method. I'll come back to that. But in principle, you can form other metrics such as like you can do an L2 distance between, let's say you have a cosmological cube and you observe data, but that's not a probability, right? It's not a likelihood that you can write down. But there's techniques that you can still use treat L2 distance in somewhat.
You calculate the distribution of L2 distance.
Yeah, you can do stuff
from
like
a
that.
bunch of simulations.
Yeah, you can do that, and
that
turns into like some ranking statistic that you can use as like inferring some information. So there are techniques that in this scenario actually still we take the emulator, we plug it back into like we still have exact likelihood for this case because there's so much cheating, but like there are a broad class of techniques that use different metrics for simulation based inference.
In the most extreme form of simulation-based inference, there's no probabilistic quantity at all. There's just a ranking of distances.
Yeah.
And it still works under assumptions.
Yeah, quote to quote work.
Assumptions.
Yeah. Anyway, but okay. So the world seems to be beautiful. Machine learning seems to be great, right? You get posterior out, you're happy, you publish your paper. That was what I thought as a grad student. If you believe us, this is to say, most of the black holes that we have observed are from cluster. The catch is, I don't really believe myself, and there is a reason for that. And so I've shown you two cases for simulation-based inference, right? One is a single event one. You give me the strain, I tell you what's the mass and
clusters.
Huh?
Globular clusters.
I think these are
Galaxies.
these are globular cluster to nuclear cluster. Yeah. So we have single event, we have also population. Now, what's the difference between them? Let's take a moment and think. Like hopefully you have like some hunch tells you that why the first example is more believable. Or if you don't believe me, the first example is more believable. Now, why? The reason why I think the first scenario is if anyone of you do SPI here, anyone have you heard of simulation-based inference before? Okay, some hands from non-faculty. Great. So there's some perks to simulation-based inference. If you have never heard of it, this is the preaching moment. Maybe you should consider doing it. Because what? It allows you to do fast inference. Once you train these things, it runs on GPU, goes super fast. All right, you get your posterior in no time. You don't need to wait almost. So that's great, right? Low retuning human effort. This is something that Ben Wando said, like from CCA. And he always said that, you know, once we have the pipeline set up, what we need to do if we want to change something, we just resimulate, retrain, and inference, right? Like, you know, it's pressing button. Who cares? It's very low effort to retune it, and it allows us.
Retuning?
Huh?
What is retuning?
Like when you want to change the simulation or change some notion of your likelihood. For example, if you look at the data, it's like, Gaussian likelihood may not be the best thing. Then you need to go back and rewrite everything and say, okay, maybe we can add a term, but it's a lot of effort. Whereas in the sense that if you want to change the simulation or change your likelihood, the pipeline is usually exactly the thing. You just like, you know, press the button and it goes.
The inference pipelines.
Yeah, the inference.
Simulation thing.
Oh yeah, that you can't get away. You still need to go code.
Can you give an idea of how long does it take to build a training set? So
It depends on problem. So it's like really hard to say. I mean, for some simpler problem, it could, I don't know, like with a sizable computer, you can do it within a day. But like for like cosmological thing, you know, there's a huge conference going on. There's like, okay, let's get our simulation down. And it's been taking, you know, some months or years. So it depends, really depends on the problem.
but in the case of the first problem,
Yeah.
the first version of this, you were sitting on all the simulations that LIGO had done, right? You got to benefit
Yeah,
from the fact
yeah.
that LIGO had already pre-simulated all the
Yeah.
events that they needed.
Yeah.
So you didn't have to do those.
Well, actually, it's not the simulation. Like people, actually, it's more like even worse than that. People have simulation, create surrogate of that, and use the surrogates as the simulation. So it's like, you know, layers of stuff. Anyway, good.
Could you elaborate?
Yes.
on that?
What do you mean? Like the surrogate part?
Yeah, surrogate.
Oh, so the way that we get our simulation from numerical relativity is that you really solve Einstein field equation, like evolve these binary forward and get the NR waveform. That takes somewhere from days to months per event. And then, you know, people have been doing this for years to create some thousands of waveform. I think it's about 6,000 now, like of them. And then people look at them and write down ansatz that, well, because gravitational waveform are actually pretty similar to each other. If you change the mass a little bit or change the spin, the weight goes change a little bit, but it's not huge. So people have been writing surrogate model, like simpler description ansatz, to trying to describe how they behave. So it's those.
So there's like an effective theory. So there's these numerical simulations that have taken millions of CPU hours, and then there's
effective
an
description.
effective description that is quasi-analytic or has
Yeah.
Scaling.
Yeah, they're all. Yeah.
And then that is the training data for your
For Max.
for your
For the emulator.
yeah.
Okay. And the good thing about SPI is like it can be very flexible because as long as you can simulate it, you're fine. Okay. Now, dangers of SPI. I like to talk about dangers more than perks. It's like fundamentally, emulator are not exact. You know, there's always noise floor that, you know, you create some emulator, it's bound to be some, you don't have infinite training time, you don't have infinite data. So you're bound to be somewhat, have some uncertainty on it. And let's imagine like I get a posterior out of my pipeline, and there's a little tail that goes through zero, okay? Some posterior mass goes to negative. So then you can look at that posterior tail like a reasonable person would say, oh, this is crazy, my machine doesn't work. Or you can go to, I don't know, like make a press release saying that, oh, we found negative mass, evidence for negative mass. But obviously you should not do that because that's crazy. But that's a real danger of SPI. You never know what's fundamental. Well, it's very hard to test and validate whether you have some fundamental assumption that you're validating, right?
Although again, this is not about simulation-based inference. It's about emulating a simulator.
Yeah. Oh well.
If you were using real simulations, you would never simulate.
Yeah.
You would never be in that regime.
Yeah. I mean, I'm putting SPI as a broad umbrella of, you know, like machine learning emulator. But yeah, like it's mostly a problem with emulator. That's like why my mass is negative. And this is really important because like when we do science, we have a specific list of assumptions that we want to like, okay, C is a constant, right? But then one day you look at your posterior, it's like, wait, C is not constant. Maybe we found something important. Well, maybe you should check your emulator. The other thing is like, are we really winning, right? So if your data is the same, let's say like in my population case, I have the same catalog of gravitational wave event until I will give us more, it's the same thing. But I have different model that is changing all the time. I mean, I only show you two model, which is cosmic, which is isolated formation, and cluster formation, CMC. But there is, I think last time that I counted, there's around 70 model that we trying to test, and different theorists will come up with the best model. And if you keep switching these models up and keep changing your simulation and keep retraining, do you really win in terms of compute, right? Because you're constantly retraining. Every time that you're training, you just get a posterior. Maybe as Mike said, just compare the simulation to that. Why you need to do emulation, right? Like so that's something to think about. When we do SPI, there's it sounds like a silver bullet, right? Because it's just like one button, you get everything. But in the end, if you keep changing a simulation, that you're actually losing.
I wasn't gonna ask.
Yeah.
Thought maybe I wasn't getting the point of what you say. So you gave the example of trying to discriminate whether they were predominantly coming in clusters or isolated.
Right.
But that has to be not a statement about individual waveforms, but about probability distributions of masses.
Yes.
And that doesn't need a simulation like this at all.
Oh, the reason why we
Like it's a totally separate question.
so the reason why, okay, there's a lot of community psychology going on in that, but so like the emulation here that we did has nothing to do with waveform. We're actually emulating, because generating one of these histogram takes some time. Okay, so what I did here,
It's just a histogram of drawing from samples
Yeah.
of relative populations of masses by somebody's model of what are mass
Yeah.
distributions in quadrant clusters or something like that.
yeah, but like they have to evolve it.
That doesn't have anything to do with machine learning.
Well, okay, so the reason why they need to do that is, so getting one of these curves you need to simulate, like, right? You need to first set up a cluster, evolve them forward, and at the end you collect them and plot the histogram. So that takes compute, okay? And if you want to come up with like some posterior, I mean, like you can sparsely populate this space and ask questions related to thought, but some people want to have a posterior. It's like, is alpha equal to 3 more likely than alpha equal to 2.5 or something like that? And what you need to do is like constantly resimulate, right? If I want to check different cluster size, basically for every cluster size, I need to rerun my simulation again. And at some point, there's a computational cost to that. And basically the emulator kind of alleviate that computational cost. You give me a set of training cluster that I can look at. So I run a set of simulation, for example, these 3. Then I create an emulator that now you can freely change instead of just being able to ask the question, is size RV equal to 2 more likely than 0.5?
But that's just really some sort of interpolation scheme.
Yes.
But that doesn't have anything to do with machine learning, does it?
Well, I mean,
think
machine
it's been
learning can be,
interpolation schemes for decades.
but like, so machine learning, yeah, I agree with you. Like, fundamentally, you can treat machine learning kind of like an interpolation scheme, but it's a very scalable, interpolation scheme. It can deal with very flexible data and it has a certain properties. Yeah, you're completely right. You can just treat this in a histogram, interpolate and bin. You can do that. But it's with machine learning, you can alleviate, really get that computational cost down to get the plot. That's the reason why we use.
And I mean, I think just building on that interpolation point, the classic interpolation methods fail when there's large numbers of parameters or
Yeah.
high-dimensional spaces.
Right.
Now, Kaze and I spend a lot of time debating whether the machine learning methods also fail in those
Yeah.
cases. However, the machine learning has a hope of working in much higher dimensions. I mean, people are literally simulating all the phases inside the Hubble volume with emulators right now. So that's like tens of millions of pre-parameters.
Yeah, I think when we say machine learning algorithm, there's like we can go on for hours for what is machine learning algorithm. What classifies machine learning is like, I mean, I would say like a support vector machine is a machine learning algorithm, or just strictly deep learning thing. So some people, they're mostly thinking about machine learning as deep learning. But to drive the point home is like, if you try to do more traditional interpolation scheme, you basically need to take every one of this spin and interpolate. Whereas the machine learning algorithm that you can pull off from the internet these days is pretty flexible. It's okay, show me a list of points, and then press the button, and it will split out some notion of histogram. So it's just computational benefit, most of it. Okay. Where is it? And then, you know, in the end, actually, you know, there are still a cost. You still need to pay the compute. I think I spent a lot of time thinking about compute. So that is an effort that not everyone appreciates. Oh, you know, it's the computer that's doing the job. Who cares, right? But there is a cost. There's a carbon footprint somewhere, some penguin size, and you can simulate this, right? So there is a cost. Don't think of SPI as a completely free lunch. It's not. It comes with a cost. But maybe that's a appreciable cost. So really, why the first scenario sounds more doable than the second? It's because the first scenario is you have a fixed model. We believe in GR. It's the same surrogate model that we can train on and keep deploying on a different number of data. We have keep new data coming in, and you just keep running the same thing, right? Good. On the other hand, the second scenario, which is a paper of mine, but so I have full authority to say this, but like, you know, you have a same catalog. The catalog barely changed. We may add one every couple of days now, but it's basically fixed data. But when you change the model, but you fix the data that you're trying to deploy this pipeline on, this is bad. You run into retraining all the time. You basically lose in the cost versus benefit trade-off. Okay, so that was the first part to just talk about, you know, some thought that I have in terms of like, if you're into SPI, burn this in your retina. Okay, if you're thinking about SPI, this is what you want.
Kaze, can I answer
Yes.
just a science question here, which is that
Yeah.
in the case of the cluster model, like in this very specific
Yes.
case, the cluster model is producing higher masses.
Yes.
And it's at the end of the day,
Yes.
is the final result basically that
Basically.
there are lots of objects at
Yeah.
high mass, and that's basically.
I think, you know, yeah, essentially. So that's something that, like, you know, after this, oh yeah, this is obvious. You know, like when I did this when I was in grad school, so, oh yeah, just use this, it'll be fine. That was me when I was thinking about SPI, amazing, silver bullet. Then we did this, like, oh, this is stupid. Just look at the mass and count, right? You can be smarter than that. The hope is, like, you know, if you have more complicated thing, maybe it's easier. But
There's much more.
you're completely right.
More like a trial problem.
Yeah, this is a trial problem. Then you have spin, something like that, you know, so on and so on. Okay, so that was oh, that's good. I'll speed run the second part actually. Now, hybrid method. So we talk about pure machine learning, simulation based, really large model and all that. It has ups and downs. Now I'm going to preach this is thing that I like more and I do more. It's called hybrid method. What is hybrid method? So we've seen this. We're back to this problem again. Give me the gravitational wave data. Tell me the mass. Okay, that's good. Now this is a hard problem. Let me look at it. Anyone can people guess like who? Actually, I said previously with the machine learning solution, we get 1 hour per event. What's people feeling in terms of the amount of hours that pours into each event from LIGO? Who's at 10? And who's at order 100? Orders 100, good. Orders of 1,000. Okay, the rest is like all the 10,000 or more.
Sure, why not?
Yeah. We're more like that. So if you think it's not why it's $1 million problem, if you know market price for CPU hours is about a cent. I think it's a cent. Well, roughly speaking, I look it up on Google. It's about a cent per CPU hours. So this translates to 100 million. So this is like told by some LIGO people to me, actually will. They told me that, you know, in 03, the last observational, we spent 100 million CPU hours on 100 events. So each event costs a million CPU hours. So it's you know, that's quite a lot of money. It's pretty sick. So the fact that we can push it down to 1 hour is great. But I'm going to show you we can push it down to 2 minutes.
What are your computers?
Huh? It's in Caltech. What's in the computer?
Oh, just that's a huge computer system.
Yeah. It's you know, 1,000 of core just going. You have 4 grad students pressing the button on, it doesn't work. It's sad. That's why I work on the problem. It's like this is sad. Well, let's end suffering. This is abuse. Now I think I need to do F5 usually. Yes. So why this is a hard problem? Let's quickly recap what MCMC is. The reason why this is a hard problem is because, well, I mean, a quick recap of MCMC is, what is MCMC? MCMC is you stand at, like, so the idea at the end is like you have some likelihood landscape, okay? You stand somewhere, let's say, currently I guess mass, I'm thinking of mass being some number, let's say 5 and 5. I'll randomly decide one direction that I want to go. This is some particular algorithm to decide that. So you propose one position, and then you toss another coin to decide whether you want to move there or not. Sometimes there's red arrow. Yeah, sometimes there's red arrow. So if you toss the coin and they decide not to move to the new place, then you stay where you are. And then you propose again, you decide whether to go there, and you just keep rinse and repeat. There's some thing, like if you want detailed explanation, go read Davis' note. It's great on why what MCMC is supposed to do. But basically, this is the process of parameter estimation. So if you keep doing this, okay, it's a little bit mesmerizing. But in the end, so this generates a bunch of samples. You keep walking in this space. You can see it doesn't spend a lot of time outside. So that's why people like MCMC, because it's pretty adaptive. In the end, you collect all these samples, form a histogram. It should look like the distribution that you're trying to sample. Okay, because I'm running out of time, I'm not going to spend too much time. But this is MCMC. Now, the reason why gravitational wave is hard is because sometimes it can be multimodality. So why is this hard? Because as I said, you know, MCMC is you stand somewhere, you propose to jump somewhere. Usually it's a local proposal. If you know a good global proposal, you have already solved the problem. So let's say you can only jump globally. What is a classical example of a local proposal? A Gaussian. You stand here, draw a Gaussian. I decided to jump there, but because the probability of accepting that jump is low, because this is unlikely to, it's not a region that you like. Okay, I'm not going to jump there. So if it is multimodal distribution, you can like walk around and just like what you saw in the previous picture. But then you mostly stay in one. It takes really long time to jump into another mode because it's very unlikely to do that. Like we can talk about this more technically. Believe me, for now, it's very hard to jump over yet with a typical classical algorithm. Multimodality is hard. Another thing is sometimes our posterior is much smaller than our prior. So if you start with like a crazy random place, it takes forever. Like you just wander around a while until you get here, then you can be more efficient. But even that. So gravitational wave is actually a pretty hard problem because of this property, how posterior to prior volume is huge and multimodality. And that's why they cost like millions of dollars. Really, you know, if you start at a random guess, right? You start with a random guess and you find the random one, they just do nothing. They just spend most of the time here until they latch onto that, and still they need to like walk around with this multimodality.
What is the multimodality for the gravitational waves? I mean, two different sources on the sky?
No, this is one sources, but like back then, like this is actually a very well-known one. So if you have two detectors like this, it could either come from downstairs or like up there. And you can actually do some smart tricks to reparameterize them, but not always. Stuff like that. Oh, and okay. So this is, hopefully I show you why this is a hard problem, why it might deserve millions of dollars, like into the budget to compute those posterior. But then, okay, how do we solve this? Like, you know, you can either build the SPI thing, what people have done, or you can do some other thing. What is the other thing? So I want to like, I won't dig into this too much. How many people know JAX already? Okay, some people, ask the people who know JAX. JAX is basically some modern computing framework in Python, pretty easy to use. It support these functionality, it supports GPU, support factorization. I'm not going to talk too much. I want to get to the algorithm and all of that. But the idea behind this is like you can write a fairly simple code, and then you enjoy all this benefit. Like run on GPU, right? Like, you know, suddenly you can do a lot more computation than what you can do. And you can compile the graph to work on accelerator. And actually, number one is very important. It allows you to just write this code as you would do for a simulation, but then now you have access to gradient. If you live in a high dimensional space and you want to go anywhere, gradient is absolutely important. So that's what JAX is good. But like, you know, I'm not going to talk too much about this. So we code up some waveform model in JAX, and we basically just recoded some of the model with some smart tricks of the gravitational wave model that we have. And now it runs on GPU. Now it's run compiled and all that. This is just a benchmark. I mean, probably means nothing. But the idea is now I can evaluate 10 to the 6th likelihood in a second because of the GPU acceleration compiled and all that. And that is actually the number of likelihood evaluation that you usually need for one run. So now if you just take this number in face value, this means I'll take this model, put it on the GPU, and now it runs, and I can finish a run in a second. There's a catch, you can't do that actually. That's why we need the rest of the talk. But the computational benefit that you can reap from AI, you know, large scale computing infrastructure that people have built could be actually quite significant. Okay.
This is really benefiting from the infrastructure of AI.
Yes.
This isn't machine learning itself, it's the
No.
infrastructure.
Yes, yes. You know, like all of the GPU acceleration and, you know, Jax knows something that actually look at the graph and compile that like a smart compiler. Those are important. And as physicists, we will tend to think, oh, let you parameterize, renormalize stuff to get stuff reasonable. But sometimes if you have a computational problem, let's think about modern computation instead of 90s computation, right? There's GPUs these days. So let's use that. That's good. Now, we can't just take this as a base value because these are computation from a GPU, which means that they're parallel. They're not serial. But as you can see in the previous animation, MCMC is a serial computation. So you can actually make most out of the GPU as it is. So you need some smart scheme to actually use all of the computation. You can't just get this in serial, right? They're different. So what do we do? So this is a package that I was asked to talk about. It's called FlowMC. It's so this is my baby. It's an MCMC package that use some machine learning to build a proposal on the fly. So this is a functionality it has, you know, built on Jax, has gradient, and then, you know, has some flow model. I'm going to show you what it does. It works for exoplanet, protein structure, and more. You can check the code out. If you ever do inference problem and you like, okay, it can be faster, talk to me. Love that. But okay, so how does it really work? As a recap, normal MCMC, when you have multimodality, you stand somewhere, draw a Gaussian around you, propose, and you start running around, right? You start moving, but it will have like, you know, spend most of the time in one mode, and it has much less probability to jump to the other one, because basically you need to go all the way here, and then you go the other way and you go back, right? It's not the most efficient way to navigate a landscape, right? So how do we remedy that? Now, remember, now we have a GPU. We don't need to run one chain at a time. We can run multiple of them. But then what we do is, like, if I have a bunch of points, so this is like training and normalizing flow. Normalizing flow is basically, if you give me a bunch of points, I'm gonna wrap a Gaussian. So I'm generating more point and more point, and I'll wrap a Gaussian to look like my point that I generated. Think about it as a very fancy KDE or fancy histogram that scale well and computes fast. That's really what normalizing flow is. Okay, so if you give me a bunch of points, I can build a PDF for you. But the problem is, let's start this and pause. Yes. Okay. So let's go back to the picture that we had before. So if I don't just have one chain, it walks around generating sample, then it takes very long time to go around, right? So if I have multiple chain, individual of them will evaluate, you know, walk around individual mode. But the problem is, let's say one chain, like one walker here, walk a little bit, generating 10 sample. Another walker here, walk around, generating another 10 sample. And you take the weight, like you just combine and do a histogram. You get half of the posterior mass here, half of the posterior mass here. It's not what you want, but you're going to see it, like, you know, right? Like there's more mass here, less mass there. So it's unnormalized. It's wrong weights assigned to individual mode. So what do we do with that? We basically, once you have that point, you build a proposal. You build the green using the sample that you generated through multiple chain. It's wrong, it's fine. Because once you have a proposal, now you can use that in the, oh god, in the MCMC to jump around. And then there is some adjustment that you can do to make sure that you're more likely to jump to this side than that side to adjust the weight. Anyway, I can go to more detail. I don't have too much time about it. But the idea, like if you know MCMC, the idea of flow MC is really you build your proposal on the fly. And this is uniquely, well, unique is probably a strong term, but it's enabled by the machine learning infrastructure. We combine the traditional MCMC with adaptive on-the-fly learn machine learning proposal, and together they can overcome some disadvantage that MCMC have, like such as multimodality. Okay, so putting like all the tools together, like this is a completely real data. The contour, I think it's the contour. No, it's just the contour. It's a reference run. That guy take I think 100K CPU hours. The contour takes 100K CPU hours, I think. This is a real data. It's the first event. Our code run on one single GPU on 2 minutes. So I think when we have this result, yeah, we were about to bring it up to LIGO and say, hey, can we have $1 million and just get a GPU, spend like $2 on it and be done with it. Anyway, so it works on real data. It also works on like a simulated population. So it's not biased. Like the right plot is show you that even we do have like a catalog of 1,500 events, it's not biased at that level. So you don't have bias and you just fast. Anyway, so like if people want to talk about MCMC more, I'm more than happy to talk about it. Now, I really want to like in the remaining 3 minutes, I want to tell you why our work. So like if you compare the time, right? People have done complete machine learning and get there in an hour. And we did some hybrid method, right? We merged the traditional MCMC with some machine learning within it. And it seems to work better. Well, I mean, better is a strong term, but you know, it seems to deliver the result in a faster time. But I don't want you to focus on just the faster time. Let's think about why does it work? In the community, we kind of known for that, and why people believe this a little bit more. I think the one thing is, so the normalizing flow, the machine learning part, make the proposal more efficient and flexible. That's nothing new, right? Like machine learning is very good at efficient compute or compute that really leverage large scale accelerators. So it's efficient, flexible, but that's benefit both from complete machine learning and hybrid method. Okay, the GPU helps, that's it. But the good thing about our sampler is fundamentally it's still an MCMC. You can run the exact robustness test, exact check as the old, you know, whatever people were using. So people don't need to go over like a mental barrier or like actually, you know, there is a generalization gap somewhere to think about, oh, this is new techniques. I don't know how I should trust the result, right? You remember, why is the mass negative case? I don't need to overcome that. It's exactly what people have been doing, but it just replace the part that is most, least understand and least efficient inside my scheme with machine learning. So I'm not trying to replace the whole thing. I'm just replacing part that's supposed to benefit from machine learning. So it retains all the good properties of MCMC. And so that's why, you know, the community trusts it. Okay, no one's here from, so no one can vouch for me, but still, take my word. And as I said, you know, it's as interpretable as generalizable. If your normal method, if your traditional method is as arcane, then okay, maybe we're doing sloppy science all the way. But if the normal method is like makes some sort of sense, then it's as interpretable, as generalizable. It has the same generalization properties as the normal method. Okay, so I think, like this is some Easter eggs that I put in. So like this is some takeaway slide, actually, but by machine learning. So you see, like, you know, the takeaway slide is pretty garbage. It's like, okay, whatever. But like, here's my takeaway. So I think if you want to think about machine learning and you're thinking about, oh, okay, let's go PyTorch and all that, you know, I know students always think about that because like, okay, I can get an industry job after this. But hold on, maybe if you want to do this for science, let's talk about hybrid method. Okay, that's if you want to do machine learning for science, talk about hybrid. Let's do it. Another thing is if you have a problem that seems to be computationally tractable, but somehow you can't get it. Maybe just think in terms of what infrastructure for machine learning that you can try. Acceleration, something like that. It's pretty easy. If you want to plot, I got you. The fourth point is in machine learning, usually there's a lot of chain, no training going on. And I think we reach a point that reproducibility is really important. I'm happy to chat more about it. Anyway, I think I'm out of time, and yeah, that's it. Yeah.
Any questions? Kaze?
So for SPI, at what point do you use real data to assess your results? Is it during the emulator part, or do you have any sort of way of checking?
You mean deployment or?
No, like how do you check the? Let's see.
I would argue you can never do that, because like what people in machine learning do is like you have a data set, right? You split it into training, you have split it into validating, right? Then you train it, you test it on like the validating or the testing set. The problem is, in science, we're always trying to go on with like something that is different from that, right? You want to study a new event, like a new system, then it's by definition outside whatever it is. How do you make sure that this is generalizable, and that you really need to put in your so-called inductive bias? And I think it's extremely hard. It's not impossible. Someone in the room is working on that, but it's very hard to validate whether your model is performing well on the real data that is potentially outside your knowledge domain. It's basically hopeless, I think, sometimes. Any other question? Yeah.
So actually, have you talked to LIGO about actually using it?
Oh yeah, they have. They're very hard.
Like, when will it be? I mean, what, you know?
Yeah, we basically need to clean up like a lot of, well, not a lot, like now it's become user friendly enough that I think they will actually adapt it for future run. But like they're running an actual experiment, so they need to freeze code, and I'm not exactly the person that usually always follow regulation. Okay, I just want to, basically my plan is like to show them a good enough start. Someone can, do the specific optimization that they want to do. It's just pipelining problem. But yeah, like as I said, I got Slack message from Max. They were telling me that we need to put this into LIGO. So yeah, let's do that. Yeah, they are in the progress of actually making that into production. The sad news is people are want double check. So they will run the new code that finish in 60 minutes or something. It's like, oh, how do we check the old new code is functional? Let's run the old code, and it's like, okay, then they still kill one more penguin by. But yeah,
It's obviously the right thing.
it's the right thing to do. Yeah. But like hopefully at some point it's like, okay, maybe it's time to put the old code. If we uncertain, then we may put up the old code. So yeah, that's you got a question?
Yeah, I don't, I'm asking a question that sounds wrong from my perspective, but I'm interested in this surrogate model. Have you thought about moving like that surrogate model? So if you really believe, maybe I don't quite understand the whole intellectual thing that's going on inside LIGO, but do they really believe the numerical relativity? Because if they believe the numerical relativity, then presumably they're bringing on some additional uncertainty when they move into the surrogate model. Yeah. And if they're living with some uncertainty going into the surrogate model, I mean, from a machine learning, I can't believe I'm saying this out loud, but you could move the machine learning earlier.
So this is a very, very good question. So it's been shown numerical relativity simulation, as if now the raw simulation, you cannot use it for 3G because we are about an order of magnitude off in terms of numerical noise. So the numerical noise that generated in the simulation are so high that like in the future, if you run the same model using just the numerical relativity, you get your systematic bias will be dominant in numerical relativity. So that's a problem.
So the surrogate model is actually cleaning up the numerical.
No, like it's worse. No, I'm not saying that. So the numerical relativity is the noise floor. Like we need to improve that, and people are working on improving that. The surrogate model has a higher noise floor on the numerical, but it's fine by now. We need to do that, and so I think you're right. Actually, there's one thing I always want to do. Like when I got the time, then I'll do it. It's like, so machine learning has been shown that all the things that I've talked about in terms of machine learning today is about speeding up. It's about paying a cheaper price for the same product. The most important question, and I think this will be critical for next generation science, is can we do more accurate can I run the simulation but enhance the machine learning that would generate more accurate numerical relativity simulation? This is an open question. You know, like across the domain of machine learning, I haven't seen one simulation that is more accurate. I think that's critical. And I think if we show that, then that will be the first moment that machine learning not only benefits speed, it benefits accuracy. This will be essential to come up with waveform and simulation that can enable, then that will be huge. But at this point, it's not there yet. So hopefully the instrumentalist has a, I don't know, crooked hammer that fucked up the instrument, so we don't need to live with the accuracy. But otherwise, we hope.
Yeah, I mean, that
The
is,
problem.
yeah, that's precision.
It's the case that there's numerical errors that cause issues at the frequencies that are detected.
Yes. Well, I mean, not right now for the detector. In the future, people forget that, you know.
Oh, for
It's
these future.
yeah. It's gonna be dominated, right? All the systematic that you have, the instrument, earthquake, all that, those can be managed. The main error that we will have in future for parameters, it's gonna come from our waveform model, and that's crazy.
But it's the standard issue in astrophysics that as missions.
I guess like, you know, like
As
Michael.
get more precise.
Yeah.
Your analysis tools become obsolete.
Yeah, well, like, but it's not the analysis, right? It's the simulation. So it's like the absolute thing that we use for stuff.
It's cool.
Yeah.
I have a question which maybe is for the audience and not you, but you referred to the GPU, the sort of efficient use of GPU.
Right.
You call it, was a big attribute of machine learning.
Right.
The way that you could think of it as being what that was. But for example, in the NYU supercomputing, are there GPUs?
Yeah.
And how do
Use them all
you,
the time.
so you explicitly
Yeah.
call them as something?
Oh, yeah.
And is everything NVIDIA?
No, it's AMD.
Oh, sick.
Because they're cheap.
And Jax works on AMD.
I don't know.
I think
Yeah, there's CUDA libraries installed, so you can use that.
I see.
like ROCm. I think ROCm is actually gonna be better for simulation. I think people have shown that. NVIDIA actually hates this. They're starting to hate float 16. They want to go down to float 8 because that's great for. But then, you know, for simulation, it's crazy. It's like unhinged. But like AMD stick with like okay, you know, float 64. So I think AMD is gonna win in the simulation direction.
Yeah. Well, NVIDIA gave us, I mean, when NVIDIA was a baby, they gave us a big computer here.
So it's very
But
old.
they don't give them away for free anymore. They can't even buy it.
There's also something called HIP. I don't know.
Yeah, HIP is AMD's programming interface, right? Yeah. I like AMD in simulation.
All right, any last questions? All right, not, let's thank you again.